Thank you for the kind introduction. At least it sounded kind. Unfortunately, I don't speak Korean. Today I'll tell you about, we've heard a lot about hardware. We've heard a lot about algorithms and applications. And what I want to focus today is about middleware. So middleware is a software that sits between the hardware and the applications or algorithm layer. And the main focus of the middleware that we'll develop at Kedma is to deal with errors and noise in quantum processors. The unfortunate truth is that this is the main, I think, widely agreed main bottleneck of this industry. We have to deal with errors. We have large error rates today. And I'll show you how we deal with them. I'll show you concrete results of how running circuits on state-of-the-art hardware actually looks like today. And also deliver a positive message that we believe that with the right hardware, with the best middleware, we can achieve initial quantum advantages very soon. And I'll say what I mean by that. So I first want to, a big part of this middleware that we'll develop is what's called error mitigation. And I like to argue that unbiased, so accurate and efficient error mitigation is necessary for unlocking these first quantum advantages and will continue to be important from that point onwards. So before, we need to be convinced that noisy quantum computation is unfortunately useless. So why is that? Existing error rates, like state-of-the-art error rates that you can expect in the coming years, are around 10 to the minus 3. Any improvement is, of course, welcome, and we'll exploit it, but that's our working assumption. And under this working assumption, when you run a noisy quantum circuit, you either are at the left side of this plot, where you have very small volume, but you can still maintain accuracy, or if you try to go to large enough volume where you can actually get to quantum advantage, where you can actually run a circuit that cannot be simulated on a supercomputer, then you see that the signal decays very dramatically, and you basically completely lose accuracy to the point where the quantum computer is just generating random bit strings and is becoming completely, naively, is becoming completely useless. So we have a long-known and important solution for this problem of errors, which is called error correction. We've heard a lot about this today in this session in particular. And error correction requires many qubits. Okay? So if I'm being really, really modest, it requires at least a few thousand qubits. And until you have these few thousand qubits, error correction is not going to solve this problem. You can generate really high-quality qubits and really high-quality, high-fidelity logical gates. But if you have just a handful of these, it's not going to be enough to compute anything interesting. Okay? So the near-term solution, the one that's going to drive us to these first applications, to the first quantum advantages, is, we believe, error mitigation. So in error mitigation, the idea is that instead of paying for errors in qubits, you pay for errors in time, in QPU time. Okay? So with investing more time, you can eliminate errors, but you don't need to invest more qubits. So this is appropriate for the current status we're in. Now, existing solutions for error mitigation are either biased in the sense that they don't get you back to the ideal value, to the ideal noise-free results. At least you don't get a guarantee, and generically that's not what happens. Or they are inefficient. So they would require a lot of QPU time to run, to the point where things that, I'll show you experiments that we've ran that took a few hours, they can take more than the age of the universe with other solutions. What I'll tell you about today is a solution that we developed at Kedma that is both unbiased, so it has a guarantee to reproduce the ideal accurate result, and is efficient in the sense that it's really close to fundamental bounds on what can be done. And so the first message is that error mitigation will drive us to these first quantum advantages, we believe, very soon. So by the end of this year, we believe we'll be able to run, or if I'm being less optimistic, by the end of next year, we believe we'll be able to run the first quantum circuits that can't be simulated classically, with partnering with the best hardware out there. And we also believe that error mitigation is here to stay. So this dashed arrow represents a gradual transition that we are working on between error mitigation and error correction. So as more and more qubits become available, we'll make use of these qubits in order to reduce physical error rates to logical error rates, subsequently mitigating these and saving in QPU time, or unlocking larger logical volume. Okay? So error mitigation is important for today, but also for the foreseeable future, as far as we're concerned. So just before we dive into the software, let me just give you an overview of the company. So Kedma was founded by Asif Sinai, who's here with me, our CEO. Dorita Aronov is a well-known quantum computer theorist, which is our chief scientist. Professor Nathaniel Lindner is a condensed matter physicist and quantum information scientist. We have 4 research teams. I lead the compilation team. You'll see what I do in the next few slides, what we're doing together. And we also have these important people who are in charge of taking the ideas, these experiments, and turning them into a real working, reliable software product. So this is the solution we developed. It's called QESEM, Quantum Error Suppression and Error Mitigation. It's also the Hebrew word for magic. And so again, QESEM is middleware. You have the user on the left-hand side. The user sends an input circuit to us instead of sending it directly to the hardware. Again, if you send it directly to the hardware, what you'll get is this very fast decaying signal, which is very far from what you want it to have. Okay? So if you send it to us, to QESEM first, QESEM interacts with the quantum processor you have access to, learns the errors that are on this processor, optimizes using pulse level access, optimizes the gates, and also enlarging the set of gates, the set of native gates, which is very significant. We then implement transpilation based on our error models. So this includes choosing the best qubits, which can be very important in a lot of different hardware platforms. And finally, we map the circuit we got to a set of circuits. That's the first step of doing error suppression and error mitigation. These circuits are then sent to the quantum hardware, and we collect the results. Again, these results naively are still useless. If you look at each of these circuits that we've sent, they don't give you the answer to the problem that you are interested in. But using post-processing, we can combine these noisy results and get the accurate ideal output up to a small statistical error bar that can be controlled. So if you want a smaller error bar, you invest more QPU time. And this trade-off between the error bar and the QPU time is what I mean by efficient error mitigation. So the hardware is the software is application agnostic, so it works for any quantum circuit with no limitations, apart from the physical limitations of what you want to do and how much time you need to invest to get it. It's also hardware agnostic, so in principle it can work for any gate-based quantum computer, and we've tested it on IQM hardware, on IBM hardware, and on IonQ hardware. We've also worked with IonQ through AWS Bracket, and got nice results that I show you in all of these platforms. We're looking forward to more collaborations continuously. And we also have now the first end users starting to use, collaborating with us to use this tool and generating results relevant for their use cases. So to summarize the advantages of QESEM over the alternatives that you have, so if you try to use our software product QESEM, compare it to the bare, you compare the maximal volume that our solution can generate, and you compare it to the maximal circuit volume that you can do if you just run on the noisy circuit directly, what you get, the improvement that you get depends on the accuracy that you need. So if you have a very low accuracy requirement, you get a 10x improvement in the circuit volume. If you're interested in quantum chemistry applications where you need this chemical accuracy, it can get to 3 orders of magnitude improvement in the circuit volumes that you'll be able to access. If you compare to alternative error mitigation solutions, which are guaranteed to be unbiased, you have this 10x improvement inside of the exponent. So we fundamentally know that error mitigation is exponential in the total amount of errors that you want to eliminate, that you want to mitigate, and therefore is exponential in the circuit volume. What matters is this prefactor there I refer to as lambda that determines the way this blow-up rate, so the way the time explodes as a function of volume. And a 10x improvement inside this exponential means that you can access 10 times larger volume. And if you fix the volume, it translates to very, very many orders of magnitude in runtime. So for example, these dots represent an experiment that we've ran, and I'll show you in the next slide. It took under an hour, approximately an hour, a few hours. If you try to run it with PEC, it would take 10 to the 40 hours. Okay, so that's many orders of magnitude above the age of the universe. Okay, so this is the first demonstration I want to share. So this was a nice collaboration with IonQ that delivered the hardware and also the application expertise. So we worked with a quantum chemist at IonQ. We worked with AWS, who delivered, supplied the cloud access to IonQ's hardware. And we supplied our middleware. And this, as full stack collaboration, generated these really nice results. So this is a VQE circuit that's aimed at estimating the ground state energy of the O2 molecule that we're all breathing right now. And so again, you see that when you run on the noisy device, you get this red result that deviates significantly from the ideal value in black. But once you use the software, you reproduce the ideal value, the exact or very close to the ground state energy, up to a small statistical error bar, which again can be controlled with the amount of time that you're willing to wait. Okay? On the right-hand side, I'm showing you more observables that are interesting in this problem, like the occupations of molecular orbitals and the correlation functions between molecular orbitals, which are used in many quantum chemistry applications. Again, you see that the noisy signal from the bare QPU, if you just access it directly, deviates really significantly from the ideal value that you aim for, but our middleware gets you back to the ideal value up to a small error bar. And this, I should mention, is, as far as we know, the largest unbiased experiment ever done, unbiased error mitigation experiment ever done with trapped ions. And as far as we know, is the largest VQE circuit ever ran on quantum hardware, and where you got accurate results at the output. OK, so this is another example, another molecule, an NaH molecule. So here we can we mitigated the entire probability distribution. So you see out of all of the 64 bit strings here, we were able to identify, you can clearly identify the large bit strings which are dominant. Here you again see the energy and a few molecular occupations. So now moving on to different hardware. These are experiments on IBM hardware on one of IBM's Eagle devices. We're now already done our first experiments with IBM's newer Heron devices, and we'll show results soon. So these experiments on Eagle devices, the first experiment here involves 40 qubits and gets to 40 CNOT layers. And again, what you see is that as a function, so this R parameter determines eventually the size of the computation, so the volume of the circuit. Okay? And as the volume of the circuit grows, you see that the circuit becomes more interesting computationally, but also becomes noisier because you see more noise. Okay? And the signal decays here on the right, you see it decays essentially to 0. So naively, the result from the quantum computer seems already useless. It looks like there's nothing to be done at this large circuit volume. But using our software, what you can do is reproduce the ideal value and get nice error bars. Here you see that when you go to the largest volumes and you fix the time, the error bar starts to grow. This is a general feature. If you want a more higher accuracy, you just need to wait more time, to give us more time. Okay? It's a resource that the user specifies for us, for the software. I want to mention that I'm measuring circuit volume here in this definition of active volume, which is the number of gates that actually affect the thing that you're measuring. So you see the shaded region outside this cone-like region. There are gates that don't affect what you're measuring. So it's really important when you think about quantum experiments and you think about the circuit volume to really only consider the circuit volume that matters. Okay? This is where the computation actually happens. Only these gates actually need to be ran on hardware. Only these gates need to be simulated when you're trying to classically simulate such a circuit. Okay? So this is a really important point. When you push the limits now here to a depth of 72 CNOT layers, this is getting close to 1,500 CNOTs in total. The active volume is almost 500 CNOT gates here. You see that we get nice results for the magnetization, this single Z. When you try to go to a larger observable, you increase the circuit volume, the error bar really starts to explode, and you see that we basically got to as far as we can go. So really push the limits with this hardware, and with our software, this is as far as you can go. I want to stress that this hardware we worked with has a 98.5% fidelity. We expect in the very near term to see hardware with 99.9% fidelity. And then this experiment immediately translates to this active volume of 7,500, which is already well above this quantum advantage barrier when you run circuits that definitely cannot be simulated classically. Okay? So generic circuits at this volume will not be simulated classically. This is a larger experiment. So here we worked with essentially the entire device, so 119 qubits, going up to 54 CNOT layers. We're showing you here the basis of the causal cone or light cone. It basically tells you how many qubits are participating. Okay? So even though the circuit is supported on the entire device, not all of the qubits are participating. This is, again, a very important thing to ask when someone shows you a quantum experiment. How many qubits are actually playing a role in this computation? So here at the largest depth, we got to over 70 qubits that are participating in the computation. So definitely above what you can simulate with a naive state vector simulation. But we could simulate this with a state vector with tensor network methods. And again, you see that we get really good accuracy, reproduce the ideal value up to statistical error bars. Again, when we try to push the limits and go to more challenging observables, you see that we are able to maintain a small error bars while fixing the time, are able to maintain a small error bar up to a certain point, and then at some point the error bar starts exploding, which again shows you the limit of what can be done today with existing hardware. And I want to stress that this limit is constantly moving forward as hardware is evolving and as our software is improving. So this just shows you, to summarize, that a quantum advantage is really close. The experiments I showed you today, if you take the reported fidelity from IBM hardware and you take our software, our middleware, you get this blue line that tells you how much time we require to mitigate a certain volume. And you see that this is above this black line that represents a classical state vector simulator running on a state-of-the-art HPC supercomputer. Now, once the fidelity drops just a little bit, already you have a crossover, and that marks the beginning of quantum advantages, the beginning of the point in time in which you can start running circuits that cannot be simulated classically. So we have a bunch of results coming up soon. And if you find this interesting, you can come visit us at our booth, send me an email, talk to us. As I said, our CEO is also here, and we'll be happy to talk about more business-oriented stuff. Thank you.
Thank you very much for your presentation. 자, 그러면 이제 Q&A를 갖도록 하겠습니다. 혹시 마지막 이번 발표에 질문 있으신 분 질문 부탁드리겠습니다. 마지막 발표라서 그럴까요? 네, 질문이 없으신 것 같은데요. 캐드마 양자 컴퓨팅은 S14, right? S14번 부스에 준비가 돼 있고요. 네, 지금 손 들어주신 분께 마이크 전달드리겠습니다.
Thank you for your talk, and I want to know what type of error mitigations are you use in this presentation?
Right.
Thank you.
So we developed at Kedma our own error mitigation method. This gives you the results that I've shown. If you compare it to things which are known in the literature, if you compare it, for example, to ZNE, then it's just unbiased, so it's provably unbiased. It gives you the correct result up to an error bar that you can bound. If you work with ZNE, it's generically biased. It just would not reproduce the ideal result. I can show you a few examples after the talk. If you compare it to PEC, which I've done in one of the slides, it's just much more efficient. Okay, so what you can do, these experiments that I've shown you are just not possible with PEC. If you try to run them with PEC, they would take a ridiculous amount of time. As I said, in some of these experiments, like over the edge of the universe. And it can be, smaller experiments would be like weeks, months. Okay, so it's just more efficient, like the amount of time you need to wait to get a certain error bar for a certain size of volume, of circuit volume with a certain infidelity is just much smaller, exponentially smaller. Okay?
네, 더 질문 혹시 있으실까요? If anybody has a question, 네, 마이크 전달드리도록 하겠습니다.
Thank you for your lecture. Is there any system impact over system overheads? Because when I use your software, how about the system impact or performance degradation?
You're thinking about the runtime or something else?
Anything.
Yeah, so the basic idea of this middleware is not to give you a degradation, but the opposite, to give you a huge improvement in performance. That's the idea. So the idea is that if you run not directly to the hardware, but go through this middleware, you get much more accurate results, or for a fixed accuracy, you get access to much, much larger volume, which is what I tried to show. The payment for this, the price we pay, and this is unavoidable, it's basically the second law of thermodynamics, is in runtime. Okay, so you tell us the circuit that you want to run, the observable you want to measure, the accuracy that you need, and the time you're willing to wait for this. So you can say, I'm willing to wait 1 hour of QPU. Okay, so 1 QPU hour, 2 QPU hours. And then we check if this can be done, or we optimize, for example, if you give us the circuit volume and the accuracy, we would minimize the time. If you give us the time, we can maximize the accuracy. but the price is in time. So a noisy computation can take, you know, a minute, and a computation with QESEM can take an hour. But the 1 minute result is eventually useless. It just differs from what you need, and the 1 hour result is accurate. So that's the trade-off here.
네. 자, 혹시 질문 더 있으시다면 질문 받도록 하겠습니다. If anybody has a question, please raise your hand and our staff will deliver the microphone. 자, 없으시다면 네, 이번 발표 여기에서 마무리하도록 하겠습니다. 자, 마지막 발표 함께 해주신 옴리 골란님께 다시 한번 큰 박수 부탁드리겠습니다.
Thank you.
Thank you.